Welcome back to the Real Number System. Today, we'll be covering section 3.4, talking about the multiplication of whole numbers. Through this section, we'll look at different models that we can use for multiplication. We'll talk about the properties of multiplication, and we'll also talk about rules for exponents. We'll talk about multiplication algorithms. We'll talk about mental multiplication skills, as well as estimation techniques for multiplication. So let's get started. Our first model for multiplication is called the repeated addition model. So what happens here is we represent multiplication by adding something again and again and again. So for 5 times 4, the 4 is the number we add, and the 5 tells us how many times to add it. So we have 4 plus 4 plus 4 plus 4 plus 4. In other words, we have 5 4s that we're adding together, and we know that this is 20. 5 is called our multiplier, and 4 is called the multiplicand. The first picture is what we call our color rods. So you'll notice at the bottom we have 4, 4, 4, 4, and 4. There are 5 purple 4s to represent 5 times 4. On the number line, you'll notice there are 5 different arrows of length 4. So that's 5 times 4. With a set, to represent 5 times 4, we draw 5 groups or 5 sets, and we put 4 dots in each set. And 5 times 4, as we know, is 20. So let's look at some examples. Mrs. McCormick puts her students into 4 groups. Each group has 3 students. So how many students does she have altogether? Our directions here ask us to use the repeated addition with sets to illustrate our multiplication. Mrs. McCormick puts her students into 4 groups, so we're going to draw 4 circles to represent the 4 groups. Every group has 3 students, so draw 3 dots in every circle to represent the 3 students. So here we have 3 plus 3 plus 3 plus 3, which is 12. Sasha puts her dolls into 6 groups, so draw 6 circles to represent the 6 groups. Each group has 2 dolls, so we'll put 2 dots in each circle. How many dolls does she have altogether? And notice that I'm using repeated addition with sets. So here we have 2 plus 2 plus 2 plus 2 plus 2 plus 2, or 12. We can also use repeated addition with number lines. Mrs. Martinez walks 3 days this week, and every day she walks 2 miles. We want to know how far does she walk altogether this week. Notice our directions ask us to use the number line with repeated addition. Typically for a number line, I'll count to about 10 on my number line. Because Ms. Martinez walks 2 miles, I'm going to take jumps of 2. And notice that she walks 3 days, so I took 3 jumps of 2, or I drew 3 arrows of length 2, and we land on 6. So 2 plus 2 plus 2 is 6, or 6 miles, that Ms. Martinez walks this week. Suppose Daphne has 5 ribbons. Each ribbon is 2 feet long. She places the ribbons end to end, and we want to know how much ribbon she has all together. Again, our directions ask us to use the repeated addition with a number line to illustrate our multiplication. I will typically count from 0 to 10 on my number line. Each ribbon is 2 feet long, so I take jumps of 2. There are 5 ribbons, so notice I have 5 arrows, and we land on 10. So 2 plus 2 plus 2 plus 2 plus 2 is 10, or 10 feet. Our second model for multiplication is the rectangular array model. So this one looks at an array of cross sticks and counts intersection points. Here's what it looks like. So notice here we have 4 rows and we have 5 columns for a total of 20 dots. So this would represent 4 times 5. So the 4 tells us how many rows, and the 5 tells us how many dots are on each row. Theo plants 2 rows of tomatoes. On each row, he plants 3 tomato plants. How many tomato plants does he have altogether? And notice here, we use the rectangular array model. So my first row has 3 tomato plants. I drew 3 dots to represent each plant. I have a second row with 3 tomato plants for a total of 6. The choir director arranges the choir in 5 rows. Each row has 3 choir members, so how many members are in the choir? Our directions again ask us to use the rectangular array model to illustrate our multiplication here. For my first row, I have 3 choir members. My second row has 3 choir members. The third row has 3 choir members, and the fourth and fifth rows also have 3 choir members. There's a total of 15 dots, so that would be 15 choir members. Our next model is called the rectangular area model. So this one makes a grid. So notice we have 4 down and 5 across here. So this represents 4 times 5. So the 4 is how many down, and the 5 represents how many across. We're asked here to draw each grid. So 3 times 4, the 3 tells me how many down, and the second number 4 tells me how many across. So I draw 3 down, then 4 across, for a total of 12. For this one, we have 5 times 2 in part B. In part B, we have 5 times 2. 5 tells us how many down, and the 2 tells us how many across. So I draw 5 down, I draw 2 across, for a total of 10. Our final model is our Cartesian product model. Multiplication can be thought of in terms of Cartesian products, similar to what we did in Chapter 2. So let's suppose we can order a burger on a light bread, a dark bread, or sourdough bread. And then we can choose a condiment, mustard, mayo, ketchup, or horseradish. We want to use a tree diagram to show the number of different orders that a customer could have. So first we choose a bread, and there are 3 breads, light, dark, or sourdough. Once we choose a bread, we choose a condiment, and we have 4 condiments to choose from. We can choose mustard, mayo, ketchup, or horseradish. If I choose the dark bread, I have the same 4 choices of condiments, mustard, mayo, ketchup, or horseradish. And if I choose the sourdough bread, I still have the 4 choices for condiments. We can write each order as an ordered pair. So I could have light with mustard, light with mayo, light with ketchup, light with horseradish, dark bread with mustard, dark bread with mayo, dark bread with ketchup, dark bread with horseradish, and so on, for a total of 12 different ordered pairs. So here, each order that we make with the server is an ordered pair. This makes our Cartesian product that we can write as B cross C. By the fundamental counting principle, we know that the number of ordered pairs in B cross C is 3 from the 3 choices of bread times 4 before the 4 condiment choices, which is 12. Suppose you plan to take 2 web-based courses at your local college. First, you can choose a history, world history, or ancient history. For your second course, you can choose a language, Latin, French, or German. Let's use a tree diagram to show the number of different schedules you could have. So first, we choose a history, world history, or ancient history. Next, we choose a language, Latin, French, or German. If I choose ancient history, I can also choose Latin, French, or German. There's a total of 6 different schedules. 2 choices from the history times 3 choices from the language gives me a total of 6 choices. When we think about multiplication using the Cartesian product model, we look at how many elements are in A times how many elements are in B, and that gives us the number of elements in A cross B. A times B is called the product, and A and B are each called factors. Because this is using the Cartesian product model, many times when we talk about multiplication, we refer to the product as the answer to the multiplication problem. Notice that we have many similar properties with multiplication and addition. So we have the closure property of multiplication for whole numbers. If we multiply two whole numbers, then we're going to get a unique whole number. The commutative property also holds for multiplication of whole numbers. When I multiply, the order that I multiply doesn't matter. 2 times 3 is the same thing as 3 times 2. The associative property holds for multiplication of whole numbers as well. Remember, the associative property changes the grouping. We also have an identity with multiplication. For multiplication, our identity is 1 because 1 times any number gives us that number. For instance, 5 times 1 is 5, and 1 times 5 is 5. We do have a couple of new properties with multiplication. We talk about multiplying with 0, and anytime we multiply by 0, we end up with 0. And we have our distributive property of multiplication. You may remember this property from algebra. So we distribute the A, and we have A times B, plus distribute the A again, A times C. Or in the second example, we'd have A times B minus A times C. Now notice that to get a whole number in that second example, B has to be greater than or equal to C. So let's use our grid model to look at how some of these properties work. Let's start with the commutative property. So I want to illustrate 3 times 4. Now remember, the 3 tells me how many down, and the 4 tells me how many across. So I have 3 down and 4 across for a total of 12. The commutative property says that 3 times 4 is the same thing as 4 times 3. 4 times 3 in my grid model means I have 4 down and I have 3 across. Notice again, I still have 12 squares. Let's look at the associative property, and again, we'll use the grid model to illustrate the associative property. So I'm going to start with 2 times 3 in parentheses times 4. Now we typically start with what's in parentheses. So 2 times 3, that means 2 down and 3 across. Now notice I'm multiplying this by 4, so I need to draw 4 of these. This gives me a total of 24. With associative property, I changed the grouping. So notice in the first set, I have 2 times 3 grouped. In the second set, I'm going to group the 3 times 4. Now again, we start with what's in parentheses. So I start with 3 times 4. That means 3 down and 4 across. I'm multiplying this by 2, so I'm going to repeat that. And notice again, I have 24 boxes. And last, let's use the grid model to illustrate the distributive property. So let's suppose I have 5 times 3 plus 4. So the 5 means I have 5 down. Then I start with the first number, 3, so I'm going to have 3 across, plus I'm going to add 4 more, and this gives me a total of 35 boxes. Now when I distribute, I say 5 times 3 plus 5 times 4. Well, 5 times 3 is 5 down and 3 across for a total of 15. 5 times 4 is 5 down and 4 across for a total of 20. And 15 plus 20 is 35. Let's look at exponents. So A is called our base and N is called our exponent. The n tells me how many times I need to multiply that a. Let's talk about some of our properties of exponents. We first have our product rule. When we multiply like bases, we add the powers together. Second, we have the power rule. I'm going to call this the power rule part 1. A power on the inside with a power on the outside, we multiply those two powers together. Now we have the power rule part 2. So notice we have the same power with the two factors that we're multiplying, and that power can go to the outside. Or vice versa, the power on the outside, see the right side of our equation, goes with both of the factors inside those parentheses. See the left side of the equation. We have our quotient rule. Again, we're going to assume that m is greater than n. When we divide with like bases, we subtract our powers. And finally, we have our power of 0 rule. Any natural number to the 0 power is 1. Our directions here ask us to write each of the following with only one exponent. So in part A, I have 2 to the 6th, 8 to the 5th, and 16 to the 3rd. Well, there's nothing I can do with that 2 to the 6th. But when I think about 8, 8 is 2 times 2 times 2, or 2 to the 3rd power. Now don't forget the 8 had that 5th power with it. 16 is 2 times 2 times 2 times 2, or 2 to the 4th power. Now don't forget about that 3rd power that was originally with the 16. Bring down the 2 to the 6th. A power to a power, we multiply. So 3 times 5, that gives us a power of 15. 4 times 3 is going to give us a power of 12, so we have 2 to the 12th. Notice here, I am multiplying like bases, so I add the powers. 6 plus 15 plus 12 is 33, so I have 2 to the 33rd power. Part B is going to take us a few more steps. So notice here I have 9 to the 4th times 36 to the 5th, and then I divide by 3 to the 18th. Well, 9 I can rewrite as 3 squared. Don't forget the 4th power that was originally with the 9. Times, now 36 I can rewrite as 9 times 4. Remember the 36 had a 5th power, so bring down that 5th power. Then bring down the divided by 3 to the 18th. A power to a power we multiply, so 2 times 4 gives us 3 to the 8th. 9 I can rewrite as 3 squared, and 4 I can rewrite as 2 squared. Again, don't forget about the rest of your expression. Bring down the 3 to the 8th. Power to a power we multiply. So 2 times 5 gives me 3 to the 10th power. Then I have a power of 2 times 5. 2 times 5 is 10, so we have 2 to the 10th power. And bring down the rest of your expression. Now notice here we have 3 to the 8th and 3 to the 10th. I add the powers of those like bases. 8 plus 10 gives me a power of 18, so I have 3 to the 18th. Bring down the rest of your expression. I can see this better if I write the division as a fraction. So notice here the 3 to the 18ths cancel out, and we're left with 2 to the 10th. Join me in the next video as we start talking about algorithms, mental math with multiplication, and estimation.